Okay, good afternoon. I'm just waiting because I'm seeing here the attendees list growing. So let's wait a couple of minutes more. Okay, now it's more or less stable, the list. I think we can start. Okay, so my name is Filipe Soares. I'm a senior researcher at INESC TEC. And I'm here today to moderate this session, this webinar, about open source tools for TSO and DSO coordination. Well, this webinar comes in the sequence of a European project, so an Horizon 2020 project called ATTEST. And I would like to tell you a few words about the project. It's an interesting project because its main goal is to develop open source tools for three big areas for planning, long-term planning, operational planning or day ahead planning, and also for asset management. In this webinar, we will focus more on the interaction. So we are talking about operational tools for TSO and DSO coordination. One interesting thing about the project that I would like to mention here is that as we are developing open source tools, we'll have three main repositories for the tools and for the data sets that are generated in the project. And data sets includes diagrams of production generation of several technologies and consumption as well, and networks, so typical networks from several European countries. And you can use it freely. They are 100% anonymized, so you can use it. The links of the repositories will be shared in the chat soon, so you can check it. But basically, we have the project website, GitHub, and Zenodo. Well, ATTEST is a research and innovation project, so it's a low TRL project. The main goal is to develop tools, as I said, so innovative tools. But even so, we have a small demonstration of the tools in a real environment in Croatia, in the region of Zagreb and other regions of Croatia that involves the local DSO and TSO. Okay, so this is the general information about the project and the context where this what you will see today was developed. Okay, now passing to the webinar and the presentations. We will have two interesting presentations about this topic. They will be 20 minutes each, so more or less 20 minutes, and then we'll have a Q&A session in the end of about 10 minutes. So write your questions or your doubts in the place, the Q&A that you have here available in Zoom, and I will try to answer to some of them, and the others I can forward the questions to the presenters. Okay, about the presentations, we'll have one. The first will be operational aspects of TSO-DSO coordination. The presenter will be Tomislav Kapuder from Innovation Center Nikola Tesla, I think. That's the correct name. If not, Tomislav will correct immediately. From Zagreb in Croatia. So it will go through different aspects of this coordination between DSO and TSO, and then it will present kind of a new perspective or the perspective of the ATTEST project. The second will be a planning of TSO-DSO shared assets, and will be given by Michael Simões from INESC TEC. So he's a researcher at the Center for Power and Energy at INESC TEC. Okay, so I think presentations are made. It's time to pass the word to the first presenter, to Tomislav.
Hi, good afternoon, everyone. Thank you, Philip, for the introduction. I'll repeat, I'm Tomislav Capudere. I'm a full professor at the University of Zagreb at Faculty of Electrical Engineering and Computing, but also a lead researcher at the Innovation Center Nikola Tesla, which is the partner at the ATTEST project. I will also have a colleague of mine. He's the main developer of the tools, of the real-time tools that I'll present today, Carlos Shepetans. So if you will have any specific questions about the modeling aspects or understanding how we model things, you can send us an email, or when we have a Q&A after the presentations, both of us can complement each other's responses. So I'll take you through the introduction, giving a general idea of what we did when starting the project in terms of establishing an ATTEST mechanism for TSO-DSO coordination, give you a conceptual overview of how this proposed coordination should work in the project, and then I'll present some both tools. So we divide them into two tools. One is for service procurement. We do this in the time frame which corresponds to, let's say, a day ahead operations, so at noon, day before the delivery, and then we have a real-time operation. So these two tools and these two system operator interactions are quite complex, but they are intervened in the project. So we have an interaction on all those levels. So in general, we are looking for a TSO-DSO coordination as a way of unlocking the flexibility, which currently we do have at the distribution level, but we don't use it. And in the upcoming future, especially with the increase of more renewables, more distributed generation, electric vehicles, storage, etc., electrified heating, and other energy vectors, we see a huge potential in the distribution level, which should and could provide system level services as well as local or global network services. So during the initial phases of the project, we sort of map what could be done in the terms of TSO-DSO coordination, some things already in the preparation of the proposals, where we define this planning aspect, the operational aspect, which we divide then into day ahead and real-time operation or operational planning and execution activation of the services, into the market aspects, functions and products, and imbalance settlement. We also have a part in the ATTEST project which deals with the asset management and state estimation. So all these small bits and pieces will be mentioned today, as they are a key input into the, let's call it, a global operational ATTEST TSO coordination mechanism. As you probably know, or you have read prior to this webinar, there are already different coordination concepts present in the literature. Probably you know about the project SmartNet. This was a sort of a benchmark project which mapped most of these TSO-DSO coordination. And as you look at these 5 different mechanisms, or 5 different main areas that are recognized, they sort of reflect the maturity of this TSO-DSO coordination market, but also the complexity of this. So, for example, you would have something which is a centralized ancillary service market model, which resembles something that we do today. So only TSO uses centrally the flexibility at the DSO level, communicates directly, and the DSO just checks for a pre-qualification. And then we have these more complex models, some which are a bit less realistic, like this local ancillary service market, where actually the distribution system operator takes on the responsibility of locally balancing the entire distribution network, to something which is, I would say, very computationally complex, as this integrated flexibility market model, where you essentially need to run the operational analysis simultaneously on both the transmission and distribution networks which is computationally something that is very intensive. You have a lot of nodes, you have a lot of decision variables, integer variables, binary variables. If you include uncertainties and multi-period optimization, this at the present, you don't really have, or we don't have the mathematical and the operational knowledge to actually do so. So out of all these 5 concepts and models, we came up with hybrids of some of them, and we call it the ATTEST TSO-DSO coordination approach. In this TSO, in our approach, we consider that both system operators can use the flexibility. We prioritize the transmission system operators' needs due to the issues of stability of the entire system. However, we also have a possibility, while the algorithms are designed in a way that the DSO, if it's not possible to provide the requested services, can bypass the service. Essentially, when you do something like this, only that integrated sharing or coordination model actually provides you a system global optimal solution. When you opt for something as we did, you get a non-optimal cost-wise solution for the DSO, as the DSO actually has to agree or respect the requested ancillary service from the transmission system operator. Our way of resolving this is that the DSO actually remunerates DSO in an extent. We sort of model this with a penalty function, and I'll show this later on. So we consider the secure and efficient distribution network operation in order to provide these flexibility services, and then this communication of what's available at the distribution level is provided to the DSO. DSO meaning that we actually, at the present situation that we have in the pilot countries that are involved in the project, requires additional communication and infrastructure for this synchronization. The mechanism is divided in 2 stages. We call them the day-ahead procurement phase and the real-time activation phase. Since there's a complexity behind these pricing mechanisms, and basically these 2 markets are decoupled, so we also decouple the active and reactive power procurement and distributed energy resources. In this context of the ATTEST, here we consider different sources. So this could be distributed generation, this can be storage, electric vehicles, or flexible load in terms of demand response. So we also consider in one of the models interaction with other energy vectors such as heat, cooling, and transport. In the initial stage, the distribution system operator calculates the range of active and reactive power from the bids that were given by the flexibility resources in the network, and it checks if the network constraints are violated. Just to show you a diagram, and I'll explain the diagram. Going first to the left-hand side picture, distributed energy resources first submit the active power bids, then the DSO does an AC/OPF calculation, defining the boundaries of available active flexibility procurement, sends these boundaries as possible active power areas to the transmission system operator, which then runs the AC/OPF in a day-ahead stage. And in this day-ahead stage, it results in, we call it a range of possible feasible areas, which need to be reserved from the distribution system level. And in case in real time the active power is being called, it will be constrained by this P down and P up. Then the DSO actually disaggregates this and sends the active reservation or the reservation of active power to the flexibility resources. The same procedure is more or less followed by the reactive power. So again, you have a bid from flexible resource. The DSO calculates all the available feasible areas for providing the reactive power. This time we fix this P down and P up coming from the left-hand side photo. So from the previous stage, the first stage, the TSO runs the ACOPF and this time sets the boundaries in terms of Q down and Q up. As a result, we actually have sort of coming from a day ahead, we have a feasible areas of reserved active and reactive power, which are passed down to real-time modules, which then check if actual active or reactive power need to be procured or actually, excuse me, need to be activated from this procured P down, P up, or Q down, Q up range. So in the real-time service operation, the transmission system operator again runs the OPF in real time. This time establishes if there is a need for an ancillary service. If there is a need, it sends a signal to the DSO. If this need comes from the distribution network, it sends this P 2 stars and Q2 stars to the DSO, and then the DSO activates the elements in the distribution network that can provide the flexibility by again running a real-time OPF. I'll give some more details on the exact OPF models in a few slides. Bear with me. This is something which is typically defined when you define a coordination mechanism. In our case, we have two system operators in charge of their own grids. The TSO is actually responsible for balancing the entire system, so both the transmission grid and the distribution grid. And on the side of the data management, each system operator is in charge of its own network. Again, in terms of reserve allocators, TSO allocates reserve in the transmission network or as a feasible range at the interface of the distribution network, but the DSO reserves or allocates the reserves to the flexibility users in the distribution network, etc. In terms how we developed the day ahead and the real-time tools, some parts of this more precise definitions of how ACOPFs were developed, especially for the day ahead stage, were given in a previous webinar given by INESC TEC. I think it was a couple of weeks ago. So Florin Capitanescu from LIST, who were the main developers of this, gave a presentation focusing on complexity aspects of these ACOPFs, the predictability, the feasibility of solutions, the scalability of the developed tools, etc. I'm just going to give you again an idea of what are the inputs. So we have different test case data coming from 4 countries, and each country has, well, for the transmission network, 1 input. For the DSO, we selected a couple of sections of the distribution network. So we have multiple cases, test case data, which, as Philippe said in the introduction, are all available at our Zenodo repository. We created the renewable scenarios, also forecasting the uncertainty of production from renewable energy storages. We also get, in case of a distribution system level, we have a request for ancillary services from TSO, and then flexibility bits which come from distributed resources. And you run a stochastic multi-period OPF model, and there's a sequential linearization algorithm which gives you a solution. This sort of is explained in the past presentation or the past webinar, but I'll repeat some things again. So the TSO coordination mechanism ensures that you do not procure the conflicting services. So for example, that the TSO needs a regulation of the voltage magnitude, but you also at the distribution level procure, let's say, a conflicting service in terms of managing congestion in the distribution network. The objective here is to minimize the overall network operational cost and you run this stochastic multi-period mixed integer nonlinear programming problem, which is solved as a sequential linearization algorithm and solved iteratively through this diagram shown on the right-hand side. At the transmission level, things are a bit more complex. As I said, we gave a priority to the transmission system operators when we designed the mechanism. So now we need to take into account a set of postulated contingencies. So we define the expected contingencies. Again, there are more renewables of a larger scale connected to the transmission network. We take into account these uncertainties, and we run the day ahead, 24-hour ahead temporal interlinks to define which generators provide the flexibility. This is formulated as a stochastic multi-period ACOPF, so constraint optimal power flow, so SPACF, and solved as a sequential linear algorithm in 3 stages, just to be able to capture these 2 bullet points first listed. So a set of defined contingencies and a number of uncertainty scenarios that we consider here. When we go to the real time, you actually pass on the signals of the procured ancillary services to the real-time tool. And in the real time, we ensure that there's a frequency control, congestion management, and voltage control in the real time at both transmission and distribution network. So we have that the TSO calculates the volume and the cost of the activated ancillary services. We developed this as a model predictive control, ACOPF. And as a result of this model predictive control, ACOPF, we get a sequence of activations, or, well, the next activation and the expected activations in the upcoming periods. Since we roll this model predictive control every 5 to 15 minutes, depending on the scenario that we defined later on in the project, and we defined which flexibility providers are activated in time step T, but you also predict the optimal future activation of the reserve allocation in the sequential time steps at the transmission level. To be able to do this, we again need a number of inputs. So some inputs are more or less the same as those for the day ahead. So for example, we take the same network data or PV, EV storage sizing and placement. So all those sources of uncertainty and sources of flexibility, we consider the activation prices of flexibility providers. The day ahead tool gives us this TSO reserve flexibility. I explained this. These are the ranges of P and Q, which come from a day ahead. And in the real time, another tool is being developed. This is not really a topic of today's talk, but we developed another tool as a dynamic security assessment. So we assess in real time what kind of contingencies occur, and as an output, we get an nadir and Rokov values, which are inputs for running the real-time tools. At the distribution network level, so we activate the flexibility from the transmission, and on occasion, the activation of the transmission level real-time tool will require activation of the distribution level flexibilities. So this transmission level tool then sends the set points at the interface to the DSO, and at the DSO level, or the distribution network real-time tool, we again run something which we call model predictive control real-time tool at the distribution level, cast as an ACOPF exact model. We have an objective function which minimizes the cost of the flexibility activation costs, but also penalizes violations of voltages or these deviations from the required set point defined by the TSO real-time tool. Different decision variables are included, such as distributed generation, up and down power, flexible loads, CVDs, storage, etc. Similar as the previous tool on the transmission, we have something which is requested from TSO, inputs from the day ahead, and activation of the activation price of the flexibility providers, and another tool that is being developed within the project, which is the state estimation of the distribution grids. This is currently much needed in the present distribution networks, as we have limited observability of the networks. Even when we do have observability in the networks, there's a chance that there's either a fault in the network or the data did not arrive. So we need to estimate the values of active, reactive power and voltages. So we define this as a multi-temporal distribution level multi-predictive control. We do not define scenarios for future time steps as uncertainty scenarios. We just define two scenarios, so high load scenario or a high behavior scenario and low behavior scenario, and sort of define, let's say, an interval within which we need to comply with the constraints of the distribution network. And just a short example of the results. So, for example, we get the request from the TSO level requesting 400 kilowatts of up power from the TSO. We run that model predictive control ACOPF, and the DSO selects nodes or actually flexibility providers. In this case, the selection came from all flexible loads on how much each device needs to provide this up power to sum up to 400 kilowatts. It also decides, so to maintain or to not violate the voltage constraints in the distribution network, it also decreases the power from these flexible loads, or actually in this case from storage units, so battery storage units. It reduces the production of reactive power by 226 kilowatts. Some future steps that we plan on doing. So this was done for 4 locations: Croatia, Portugal, Spain, UK. Again, the anonymized networks are available on our Zenodo repositories. Very soon, in the upcoming months, we will also provide so-called enriched networks. So we developed a tool which enriches all of these networks with flexibility provision, but also with additional low carbon technologies such as PVs, EVs, etc. And we will run the simulations showing what benefits we can achieve from coordinated operation of TSO and DSO. And we will define some KPIs. In case of our tools, they are defined as technical operational costs and environmental benefits. And as the last thing that we are currently setting up, not for 2030, 2040, and 2050, but for the present case study, so 2023, we will have a live demo, a small live demo. We will have a real data streaming from Croatian transmission system operator and distribution system operator, and we will, with that real-time data streamed from the system operators, we will put our tools to work and to do what actually we showed you in the past couple of slides. So running the tools, we will not activate, so there will not be a closed loop activating the flexibility devices, but the platform that is being developed by our partner SoftLab will suggest the activation options to reduce the cost or to improve the technical constraints of the network. That's in general it from the presentation. I thank you for your attention, and later on, I'm sure Philippe will pass me on a couple of questions that I see you posted while I was presenting. So thank you.
Thank you very much, Tomislav. In fact, I already have here several questions. Okay, well, let's skip to the schedule and let's pass to the second presentation. So thanks once again. I will forward some of these questions to you and you can reply in the end. So the second presenter is Michael. So Michael, I think you can share your screen and unmute yourself. See if it works. Okay, so the floor is yours, Michael.
Hi everyone, can you hear me?
Yeah, perfectly.
Okay, good afternoon, and thank you for attending this webinar. The tool that I will be presenting was also developed within the ATTEST project, and it concerns the planning of shared resources to be used by TSO and DSOs in this context of a TSO-DSO coordination scheme. So this is the outline of the presentation. First, I'll go through the motivation, then I'll go through some of the TSO-DSO coordination mechanisms that were proposed in the literature, and then I'll present the ATTEST TSO-DSO coordination mechanism, the role of energy storage systems in future power systems, then I'll present the proposed tool and a small case study with some results, and then I conclude and talk about a bit future work. So motivation for this type of tools. After the liberalization and unbundling of electricity markets in Europe many years ago, electric transmission and distribution systems have been independently managed by TSO, DSOs, and this was performed based on oversimplified models of each other networks, and distribution systems essentially became passively operated. However, currently, electric power systems are currently experiencing a profound change with the integration of renewable energy sources, especially inverter-based, both at the transmission and distribution levels, distributed energy resources, such as energy storage systems, electric vehicles, and active or flexible consumers that have started to participate in network operation, and with this, the deployment of active distribution networks. And so to really take advantage of the flexibility that is growing, especially at the distribution level, coordination and active interactions between TSO and DSOs are required. It is expected that the exploitation of these resources will facilitate the integration of renewable energy sources at lower costs for consumers by reducing the need to procure ancillary services from conventional generation, reducing investment costs, such as in typical reinforcement, improving asset utilization, as extending the lifetime of transformers, for instance. However, this comes with several technical and regulatory challenges. From a technical perspective, the management and coordination of a very large number of flexible resources that keeps growing is very complex. Second, the roles and responsibilities of the involved market participants, such as TSO, DSOs, aggregators, and so on, must be clearly defined or redefined in some cases. And third, ultimately, TSO and DSOs are autonomous control entities with their own rules, policies, and objectives, which may often conflict each other. And so in this context, TSO-DSO coordination mechanisms were proposed in the literature, and this can be broadly classified into centralized schemes, where the TSO or an independent system operator has access to all the resources present in the network, both at transmission and distribution levels, or decentralized schemes where the large-scale problem is decomposed into smaller problems, typically DSO network and TSO network. And here, within decentralized schemes, we can also categorize them in two main approaches: hierarchical schemes or distributed schemes. Hierarchical schemes are those who follow a typical leader-follower organization. This is each agent or subproblem performs local decisions that are communicated to the next hierarchical level. And within this context, the SmartNet project, as Tomislav referred already, proposed a set of 5 coordination schemes that were widely adopted in the related literature. or distributed schemes where agents or sub-problems must reach a consensus regarding common or coupling variables. For instance, active and reactive power flows at the interface between transmission and distribution systems and voltage magnitude values. The advantages of decentralized schemes have made them very popular in the field, with centralized schemes rarely being used. And so, as Tomislav already presented, ATTEST proposed a new coordination mechanism, which draws some characteristics from the coordination mechanisms proposed by SmartNet. Here we consider local markets for the distribution network, and the main feature here is that active and reactive power bids are decoupled. And so what will be the role of energy storage systems in future power systems? For high levels of renewable energy and consumer participation in power system operation, the balancing task will become more complicated, and effectively dealing with the uncertainty derived from these resources will require more flexibility in the system. Energy storage is a way to increase that flexibility. Therefore, their ability to deal with uncertainty is recognized as a valuable means to provide additional system security, reliability, and capacity to respond to changes that are difficult to accurately forecast. The increasing uncertainty associated with network operation creates new opportunities for energy storage systems at different levels of the power systems. However, energy storage systems are still very costly. It's still a very high initial investment cost, and it's more likely that this will be deployed by third parties due to the unbundling regulation that we currently have in Europe. And so, what is the current state of energy storage planning tools? Most of the published work is mainly focused on the optimal investment, but it's either from an independent investor, DSO, or TSO perspective. Only recently, the models have started to consider more complex topics such as energy capacity degradation, which is something that is very important in energy storage planning, full AC model of the power flow equations, or uncertainty associated with the operation of the network, such as market price forecasting or operational forecasts, such as load and renewable generation. Little to no research has been published on the joint planning of energy storage systems. And so what are we proposing here with this tool? It's essentially a planning tool for shared energy storage systems that can be installed at the interface between transmission and distribution systems. The investment is performed by a third party, what we call the energy storage system owner, and the shared energy storages can be used or simultaneously used by TSO and DSO for the operation of their networks. Furthermore, it is considered that the ESSO can participate in energy and secondary reserve markets, and a battery capacity degradation model is considered in the planning procedure. It is a stochastic bi-level planning tool, and I'll show you a diagram of the tool in a few slides, where at the upper level, investment decisions are determined, and at the lower level, we simulate the operational planning between TSO and DSO, considering the ATTEST coordination mechanism. We apply some mathematical decomposition techniques to keep the problem tractable and to keep the data privacy of the several agents involved in the optimization procedure. So this is a diagram of the tool. As I explained earlier, at the upper level, we perform investment decisions. So power and energy capacity to be installed per year in the node, subject to budget, energy capacity, and power to energy ratio constraints. Energy capacity constraints are related to the space that is available at the substations between transmission and distribution to install energy storage systems. Power to energy ratios are related to the technology of the batteries themselves. At the lower level, we simulate the coordinated operational planning of considering the ATTEST coordination scheme. This is a diagram of the operational planning scheme, how it was implemented, how it was mathematically implemented. So essentially, the objective here of the TSO is to minimize operational costs. Objective of TSO of ESSO is to maximize operational revenue from using the batteries to participate in energy and secondary reserve markets. And the objective of TSO is to avoid problems, congestion problems at the distribution network level while supplying services to the TSO. This coordination scheme is relatively complex when compared to other coordination schemes proposed in the literature, such as hierarchical schemes, but it has several benefits. First, it considers the existence of shared resources that can be simultaneously used by TSO and DSOs, and that these resources, in this case, battery energy storage systems, can provide additional ancillary services, such as frequency reserve. And second, it reflects the full potential of the flexibility that is available at the DN level. This because it considers the intertemporal constraints of the distributed energy resources, such as energy storage systems. As we know, if we activate some flexibility now, the flexibility that that resource can provide in future time instance will be impacted, and this coordination scheme reflects that. And secondly, it also considers the impact that voltage magnitude has at the distribution level to provide flexibility to the TSO. This is especially felt when no old OLTC transformers are installed at the boundary between transmission and distribution networks. And so now we have here a small case study. It was performed for an area of the Croatian network corresponding to Koprivnica region. The data was provided by our partners from the project, and it's available in our repositories. In the total of 5 active distribution networks were considered. 4 representative years were considered, with 1 representative day per year, load growth of 1.25%, and flexibility growth of 5%. Power to energy capacity ratio corresponding to lithium-ion batteries and the calendar life of 20 years. Maximum installable capacity of 2.5 megawatt amp hours. The costs were obtained from the National Renewable Energy Laboratory projections for utility scale battery energy storage systems. This showed the convergence characteristic to the left of the problem. It took approximately 104 iterations to converge. And to the right, we can see the investment plan in shared energy storage systems. As it's possible to see, ESSO tends to invest in energy storage systems towards the end of the planning period, not in the last year, because since the energy storage systems have a lifetime of 20 years, it's more profitable to install in 2040. And this is when also the problems in the network really start to show. And here we can see to the left the voltage magnitude at the interface between transmission and distribution networks, and how this evolves over the planning period. As it's possible to see, the fluctuations increase a lot, especially until 2040, and between 2040 and 2050, this remain approximately the same, which can be explained by the fact, if we look to the right side, that in 2050, we can see that DSO provides reactive power support to the TSO. Here are some results obtained for the shared energy storage systems. As it's possible to see, in 2020 and 2030, it's really not profitable. Well, we don't have installed capacity, almost no installed capacity in shared energy storage systems. The secondary reserve that the SSO can provide is higher in 2040 than in 2050, because in 2050 the batteries already show some degradation. Here we can see the flexibility usage both at transmission and distribution network level. As it's possible to see, the flexibility usage from private consumers will increase exponentially, but this is much more drastic at the distribution level. This is because over the planning period, distribution networks will use this flexibility not only for local management, but also to provide services to TSO. On the bottom, we can see the evolution of losses, energy losses over the planning period. As it's possible to see, at the transmission level, it will increase pretty much on a linear basis, so much less than what would be expected, since the load growth is exponential. And at the distribution level, losses actually decrease until 2040, and in 2050 increase slightly again, but to a value that is lower than in 2020. So this shows that these coordination mechanisms can be beneficial not only for distribution system operators, but also transmission system operators. And so, with this work, we proposed a new TSO-DSO shared resource planning tool under a new TSO coordination mechanism that was proposed by the ATTEST project, and it was extended to consider the presence of these shared resources. We've also shown that TSO and DSOs are able to coordinate their operation in the presence of shared resources by sharing a relatively small volume of information, and that this coordination brings several benefits to the operation of the overall power system. The proposed coordination mechanism can also provide additional ancillary services that are often disregarded in the TSO-DSO coordination mechanisms proposed in the literature, such as frequency regulation reserve. In the future, we intend to study additional services that these shared energy storage systems can provide, and study the application of convex OPF models to the operational planning subproblems, with the objective of studying the convergence characteristic of the problem. Yeah, so this is all from my side. Thank you for attending, and I'm open to questions.
Thank you very much, Michael, for your presentation. Now let's pass to the question and answers session. We have many questions. I tried to reply to some of them. Is here another one that I will try to reply very fast, which is there a mathematical definition used to quantify flexibility? What are the units of flexibility other than megawatt hour? So in fact, if we look for a mathematical definition, there are several. The most common, if we consider only an instant of time, is the flexibility that you have to increase or decrease the power of the operating point of a device. But then there is more complex definitions of flexibility, for instance, for a battery that have intertemporal constraints. So, but you can find several of these mathematical formulations in the literature. Okay, so among these questions, some of them are very complex. So they are discussing, let's say, the entire scheme of coordination. So I will skip some of these questions because otherwise we will need another webinar just to clarify them. And I will focus on some more specific questions related with the tools, and I ask both presenters to try to be very fast in the answers. So there is one here, I think it's for Tomislav. Are there any other methods except TC-OPF to find the boundaries, flexibility areas of DSO and TSO?
Yes, I think the ACOPF method is the most researched one and probably the most exact one. There are more primitive ones, like you can run sequential power flows, changing the powers of different devices. But recent research focuses on ML methods, which are quite fast and more scalable than, let's say, ACOPFs for large networks.
Thank you, Tomislav. Another one for you from Angel Paredes. So he's from Malaga, so it's Spain. It says that the example was for one single DSO. Would it be possible to integrate multiple DSOs which want to procure flexibility to upstream TSO at once? So
Okay,
multiple
the
DSOs.
example was simple to show the case. And yes, in one of the papers published by authors from ATTEST, guys from LIST, we actually substitute passive loads at the interface with multiple. So at multiple node points of the transmission network, you have DSOs modeled. So yeah, it's possible. We tried, we did this. Of course, you need to keep in mind that when you do something like this, so we do not really model this as a centralized model run. We do not run all the models at a time. It's more like a sequential or an iterative run of all these 4 models that I presented. So basically, if we are talking about the day-ahead or real-time tools, yes, you can do it, but there's always when you do these parallel runs of multiple distribution networks, you always have these issues which come along with large networks with a lot of binary or integer variables, which come along with, if you have, for example, in real-time tool, an exact non-linear problem. So all these things bring complexity to parallel runs of multiple DSOs. And of course, even when you go from, I would say, 4 or 5, well, depending on the number of nodes and the number of integer binary variables, you can't run this on your personal PC, so you need something quite stronger to computationally manage this.
Okay, thank you, Tomislav. Another question from Muhammad Javadi. So thank you for the presentation. Regarding the implementation of TSO-DSO optimal power flow, so I think it's for Mikhail. Is it running as a decentralized optimization problem or using an iterative process with updating P, Q, V, and delta at each connection point? And why the P and Q are not determined at the same time? Well, I could answer, but Mikhail, perhaps.
This is not a question for me.
No, I think it's for Mikhail, this one.
Okay.
I think it's for Tomislav, actually.
It's for, yeah, it's for Tomislav.
I was talking about this, that's what I assumed. So I answered the first part of the question. So we do not run this as a centralized, but it's a decentralized optimization problem. So we run, as I explained in the diagram, we run the DSO day-ahead as a pre-qualification, then the DSO day-ahead optimal power run, then a day-ahead DSO run, then you move to a real time. So each 5 minutes you run a TSO model and then sequentially, iteratively, if you like, a DSO model. So at the real-time level, we do not decouple P and Q. They are run, the decisions on P and Q are run simultaneously. So you have a full exact ACOPF model. For decoupling, so why I said they are not determined at the same time, mostly because of the issues that we had with the ACOPFs at the day-ahead transmission level stage. So we tried to make it a scalable, large-scale model for, I think it's 100,000 nodes or something like this. Philip, you might now know the numbers. But we also consider a large number of possible contingencies, a large number of uncertainty scenarios for multiple nodes where we have renewable energy sources. And then you have binaries for let's say, flexibility providers such as electric vehicles, etc. So this brings complexity, and it's computationally demanding to run P and Q at the same time. With decoupling at this transmission level, we actually get these linearized models, which are scalable, and we can run them on large-scale systems.
Okay, thank you, Tomislav. Now I understand my confusion. Sorry, I didn't focus on the question. I tried to map the questions with the presenters, and there is another one from Muhammad Javavi that is for Mikhail, and I took here note Javavi for Mikhail. Okay, so Mikhail, this one is for you. It's also from Muhammad Javavi. The ESS, or the energy storage system, can work in 4 quarters: inject, absorb, P and Q. In the shared model, how will the operator manage the optimal operation of the shared battery to maximize its benefit? Can you may have a quick, because he says that there are some conflicts between minimizing TSO, DSO cost and the storage system profit. Can you try to give a very fast answer?
Yes. So, in fact, energy storage systems can inject and absorb both active and reactive power. However, in the simulation that I presented, it was only active power that was considered. But so, essentially, what happens is that TSO, DSOs, and the SSO must coordinate their operation. And so, in the end, the result that we will obtain is the result that is best for the overall system. That's essentially well, the answer. There's no specific priority in this case.
Okay, thank you, Mikhail. We can try another one, which was here. It's also for you. So which kind of decomposition technique is used in the proposed tool?
So at the coordinated operational planning stage, we applied the alternating direction method of multipliers.
Thank you. Okay, so we have here, so don't understand me wrong, the questions that we didn't answer are very interesting, some of them. But the problem is that we will not have time to discuss them for sure. So what I suggest now is that you contact directly Tomislav and Mikhail, so you will receive the information of the session and the record of the session, so you can watch it again. I suggest to send an email directly to the presenters, and I'm sure that they will clarify all your doubts about the topic. Okay, so to finish the webinar, I would like to thank you all again, especially to Tomislav and to Mikhail as presenters, and also to all the attendees. Thank you very much, and thank you for the questions. They are really interesting. So thank you very much. You will receive the recording after by email. Thank you very much again.